In this tutorial, we're going to be taking our scene from part 1, creating a character on it, and then anywhere we click within the level, our character will move to that location in the most efficient way. We'll also have some basic understanding of height, so our character can't jump yet, so he will make the long way around these higher points instead of going straight through it. So yeah, let's jump into it. Hello, welcome to part 2 of grid-based movement with Pathfinding. My name's Aaron, and I'm making the tactics game. In this tutorial, we're going to be focused on creating a pathfinding algorithm using A*, and if this is something you want to follow along with, down below there is a link to the repo and you can download this project including the finished scenes and follow along with us. If you have not seen part 1 or if you're using your own stuff, your own project, that should be completely fine. This is what we're going to be covering today is fairly generic and it should work for whatever it is that you want to use it with, I hope. Let me know if not, but I hope everything here will be pretty generic. But yeah, that is everything I want to say. Let's jump into some coding. So what is A*? A* is an efficient pathfinding algorithm used in a lot of games that utilizes 3 variables: the G cost, the H cost, and the F cost. And it's fairly simple. The G cost is the distance from the starting node, H cost, distance from the end node, and F cost is the G plus the H. So how it works, as a very basic example here, is that when we start our movement, so let's say our character here wants to move to this green square, we will check all of the tiles or nodes surrounding that character. We will get the G cost, the H cost, and the F cost using the G and the H cost. And then we find the value with the lowest F cost and we put that into our target list. Next up, we repeat it again until eventually we find a path that leads to our target. And that is kind of it. We're going to be programming this from start, so hopefully I'll explain a little bit better while we're programming, but that's basically as basic as I can make it. Here we are back in our Unity project, and in our starting scene that we just finished off after part 1, where all we have is we have a map, we generate a grid on top of the map, and we can click to interact with our tiles. I have skipped ahead a little bit, and I have just done when we click, we will now spawn a character, just to make this as efficient as possible. There is one thing I want to display. I'll go over now quickly how I spawn the character just in case, but there is one thing I want to point out on a rendering tip that I want to point out to you, and that is on this tile here in particular, our character needs to be rendered behind this tile. I've touched on this a little bit in part 1, but our character needs to render behind this tile, and currently he isn't. And the reason that that's happening is our character's pivot point and Z is aligned with this tile's center and Z. So Unity doesn't know which one to render first. So in this situation, our characters are being rendered in front of it. But we want our character to always be behind reliably. And there's a very easy and lazy way to do that. And that is by just slightly offsetting our character's Y position. So if I go into our character's Y here, and I just give it a very small value of 0001, and now our character is rendered behind correctly. So we're going to do that in code as well. Here in the mouse controller from part 1, I've made a few little changes to get our character spawned. So I have a character prefab and a character object. When the first time we click, we check if the character is null. If the character is null, we create the character and position him on the tile we want. It says position on the line. That's a typo. On tile. So we'll create our character and we'll position the character on the tile we've clicked on. Positioning is basically the exact same as what we've done for our overlay tiles, where we just give it a position. We give it the same position as our targeted tile. We give it the same sorting order as our targeted tile. And we also let the character make a pairing between our character and let it know which tile it's standing on. And what we're going to do here now is what we just did. We're going to increase this by 0.0001 F. And it's kind of ugly, I admit. And if I was going to do this in more than one object, I would probably find a better solution for this, but because for the sake of this tutorial it's only one object, this is what I'm going to do. So it's just a little tip for you to explore if you experience something similar. You could avoid this by careful map design, and now our character renders correctly and it looks great. And also the only other thing about this character is on our prefab we have attached a very basic script that just has our overlay tile attached, that has a reference to an overlay tile. So pathfinding, we need to get into pathfinding. We need to write a pathfinding script, and we're going to jump into that right now. The first thing we need to do before we can start writing pathfinding, we need to have the concept of a node within our put within our project. And luckily enough, we already have a script that is ideal for this, and that is our overlay tile. So what we need to give our overlay tile is we need to give our overlay tile a G, a H, and an F cost, and also knowledge of its previous tile if it's a part of a path. Let's jump in and let's get that done. First up, we want a public int. We're going to call this G, public H, public int H, and our F is a public int F. And because our F is just a combination of our G and our H, we're going to do where get up for F, and it's going to return G plus H. So now we have our G, H, and F cost. We want to know if our tile is available. So we're going to have kind of the concept of it being blocked. So an example of why a tile would be blocked could be if a character is standing on it. We want to block that tile. So we're going to do a public bool as well, and that's going to be called is blocked. And also we want our knowledge of our previous tile in the situation that this is a part of a path. So I'm going to call this previous. And that should be all we need for now for our pathfinding to get started with our pathfinding script. So let's jump into that right now. Back in Unity, we're going to create a new script. I want to call it Pathfinder. And this script does not need to be a mono behavior. It's just going to be attached to our controller, our game controller. So we can remove mono behavior, and we can remove the start and update. So let's write our first method, and that's going to be public, our find path method. So that's going to be a public list. It's going to return a list of overlay tiles, which is basically going to be our path, find path. Overlay tiles or nodes, I guess, in the technical naming convention. This needs two things. This is going to need an overlay tile, a starting node, and overlay tile, or end node. So where it's going to be and where it's going to go. After that, we need two lists. So we're going to need an open list and close list. So list overlay tile, open list equals new list overlay tile like that. And another was copy and paste this, and close list. And what these are is our open list is basically a list of tiles that we want to check in the next iteration of a loop. And once we're done checking a tile, we add it to our close list. We don't want to recheck tiles if we don't need to. So let's start with, we're going to add our starting point to our open list. Open list.add, and we're going to add in start. Now what we want is a while loop, and we're going to keep looping until our open list is empty, which basically means that we have no more tiles to check. So open list.count, or count is greater than 0. So while our list is greater than 0, we're going to keep looping through this for it. Now what we want to do is we're going to find the lowest, at the very beginning, we're going to find the overlay tile with the lowest F cost. So we're going to do overlay tile, and I guess current overlay tile. This is our next selected node for the path. We're going to order this by, let's include link, which is a list manipulation library that is very powerful. And if you don't know what this is, I recommend you learn or just follow along with this tutorial, and you'll figure out some of the power of it. First. So this is giving us the overlay tile with the lowest F within our open list. Now, it of course doesn't make sense right now, but this is our recursive loop. So we're going to be doing all of our calculations at the bottom of the loop. Once we have that tile, now that we've kind of satisfied that this is our tile that's going to be in our path, we can remove it from our open list. So we can do open list dot remove current overlay tile. Then and we're going to add it to our close list dot add current overlay tile. Okay. And then we want to do an if our current overlay tile equals the end. So have we found our final point? We're going to finalize our path by stepping through all the tiles again, and with our parent, with our previous tile that's attached to our tiles. Now, once we've kind of figured out if this is our end tile or not, we're going to want to find all of its neighbor tiles so we can check them in the next loop. So we need a function that's going to get our neighbor tiles for our tile. So we're going to fire neighbor tiles equals, I'm going to create a new method called get neighbor tiles, if I know how to spell neighbor correctly. Neighbor tiles, and it's going to take in our current overlay tile. Let's go to here, let's generate that method, and this is basically going to be just lots of 4 duplicated if statements. So we're going to need our map that we created in part 1. So in our map manager, we have a dictionary that references all of the tiles within our map that we can easily check now to get other tiles. So and in a singleton. So to get that now, all I need to do is do map. We use map manager dot instance dot map. So now we have a reference to all of our tiles within our level, and we're going to have a list of overlay tiles. I want to call this neighbors. It's new list of tiles. This is the list we're going to return, and now we want to check our 4 neighboring tiles and get a grip of them. So we can do. So we want to have a. We're going to get a vector to int. This is our location to check. That's going to equal a new vector to int, and it's going to be our current overlay tile dot. Oh, we need one more thing in our overlay tile. We need to have the concept of our. We want to know what our grid location is, not so the vector 3 int version of this tile's location. So we're going to give this a public vector 2 int. I think is all we need is vector 2 int. We want vector 3 int. I think grid. We might have to come back and change that, but for now, let's do that. Grid location. And also where we instantiate overlay tile, we want to give that a value. So down in our map manager where we are instantiating our tile, we're going to do overlay tile dot grid location equals tile location, which is gathered from this loop up here if you don't have this project. And now from there, what we can do is we can do grid location dot x, and we can do the exact same thing, grid location dot y. We can probably next line these. And now we're just going to do, so let's do say y plus 1 here. So if I put a comment here, this is basically our top neighbor. And we just do if our map contains key, because it's a dictionary, we can just do contains key, and that's going to location to check. So we are not at the bounds of our map. This tile does in fact exist within our map. We are going to add it to our neighbor. So neighbors.add our map location to check. Okay, and now all we're going to do is we're going to take this and we're going to duplicate that 3 more times. So instead of top, we want our bottom. So bottom, and that means y is going to be a minus. Get rid of this. Then we want right. So we can get rid of this from a y, and we can do +1 on the x instead. And finally left here, and to get rid of this, and we do a -1 on the x. And that should give us 4 tiles within our neighbor. Also, we need to return neighbor at the end. Now we have our neighbor tiles. We want to check that these neighbor tiles are valid, and if they are valid, we're going to add them to our open list. So we're going to do for each. That's for each neighbor in our neighbor tiles. Don't forget to change my generated method to return the correct thing because I forgot to do that. So it returns list of overlay tiles. We're going to do a for each through our neighbors, and we're going to have an if here to check if this tile is valid. So we're going to do if neighbor. We want to check if it's blocked. So if for whatever reason, or we want to make sure that this is not already in our closed list. We don't want to go backwards in the list. So close list dot contains neighbor. Make sure. And finally, we want to have a basic understanding of height within our game. So our character isn't going to be able to jump. It's going to have to go around the long part on the taller parts. So we're going to do that here as well. And what that is going to be is that we're going to check the Z axis compared to our current tile to see if it's valid or not. So we're going to do matf.abs. So matf.abs, we're going to do current overlay tile dot transform current overlay tile dot grid location z minus our neighbor dot grid location dot z. We want to make sure that this is not greater than our jump height. So our character's technical jump height. So in this example, 1 is going to equal your character's jump height when you eventually implement that. That's not for this tutorial, but that is basically how we're going to do that. So now that if the character is not valid, all we're going to do is continue. So this tile isn't valid, it's not going to get added into the open list. Next, what we need is we need to calculate our G, H, and F cost on our tiles. So to do that, we're going to need to calculate something called the Manhattan distance. So our G and H cost is not a direct distance. It's going to be something called the Manhattan distance, which is basically the distance using blocks. So it's not going to move in diagonals. It just moves in like ups and lefts. I think it's called the Manhattan distance because in Manhattan, I guess, they use a block system, which I thought all of America could use the block system. So I don't know why it's called Manhattan, but that's why from what I learned Googling. So we're going to do neighbor.g is going to equal a new method called get Manhattan distance. And that's going to take in 2 things. It's going to take our starting node and our current node, I guess our neighbor node. We generate that method, and this is super simple. some super simple maths that I definitely didn't Google. So we're going to return mathf.abs, and what this is going to be our x locations minus plus our y locations minus, and that's all it is. So start dot x dot grid location dot x minus neighbor grid location dot x plus, let's copy this bit and change these x's to y's, and with that we have our Manhattan distance, and that's it. That's all that is. Let's copy this line, and we're going to do the same thing for our h, and here we're going to put in end instead of start, and that is our g and our h calculated. And remember, f is just a getter that combines both of those values together. And finally, all we need to do now is we're going to do if our open list does not contain this tile. Again, we don't want to have accidental duplicate tiled neighbor. We're going to add the neighbor. Open list.add. If nothing works out, we're going to return a new list of overlay tiles. So it's going to be just an empty list. And now the last thing we need to do is we need to finalize our path. So we're going to need a new method that's going to return, and it is going to be called get finished list. And we're going to give it its start to end. Also, I forgot one thing down here. We need to set our neighbor's previous. So previous, and that is going to equal our current overlay tile. So what we're going to do is in our finished list, we're going to basically step through all of the previous's and have our get our path from that. So let's generate our method. And what do we need in this? We need our finished list. So we're going to need a list overlay tile finished list equals new overlay tile list overlay tile, and we need a current tile to start with. So overlay tile current, this is going to be a reference to our end tile. Current tile equals end, and we're going to do another while loop now. While our current tile does not equal start, okay. And all we're going to do is we're going to do our finished list dot add current tile, and then we're going to do current tile equals current tile dot previous. So hopefully you can understand what's happening here. When we are literally just going through, we've established the best possible path, and now we're just going to loop through all of the past nodes that they've traveled along to get there, and we're going to return that now to the user. And because this has been because of the way we've looped through, our list is actually reversed, so we want to reverse it back. So we're going to do finish list reverse, and finally we're going to return. Hang on, calm down. Return a finished list, and that is a pathfinding script done and dusted, and that should be working hopefully. Famous last words. So let's get this implemented in our mouse controller, where we are currently controlling all of our controls. We're going to have a private pathfinder. Let's call it pathfinder. We need to add a start to instantiate the pathfinder. So in our start, it'll be pathfinder equals new pathfinder. Beautiful. And now down here, what we can do is we can do else, because we don't. So on our first click, we're going to create our character. On our second click, we're going to start moving. So else, we're going to get our path. So var path equals pathfinder find path, and our start is going to be our character's current location. So character dot, and we know what tile from our character is standing on from this character info script. Okay, and we know the current tile we're focused on from this code up here. So let's just take a little break and let's do some debugging and see if this is working correctly and if we get a list. So back in Unity, we're going to press play. We spawn our character, we click, we check our path, and we have a count of 3, which I think is pretty correct. Path of 3 tiles, which is probably correct. So let's move on and let's actually get our character moving and see if it is correct. So how are we going to get our character moving? In our mouse controller, we're going to have a new public variable. I'm going to call it speed. Let's put it at the very top. Public float. I want to call it speed. And we're going to set this path also to be a private variable up here. So we're going to do private list of overlay tiles. We'll call it path equals new, just like that. Now what we can do is, if there is a path exists, we're just going to have our character always moving. So if path count is greater than 0, we're going to move with a new method called move along path. Let's generate that method, move along path. And for this, we're just going to use Unity's built-in move towards function. There's also lots of ways to get a character moving, but for this, we're just going to use the move towards function. So we're going to do var. We need something called a step, which basically understands how much we move each loop. And that's going to be speed times time dot delta time. Now, because this is a 2D game and not a 3D game, we need to use our vector to move towards. But because for our rendering we're using Z, we need to be able to capture our Z axis as well. So by default, vector to move towards will set the object's Z to 0 because it doesn't care about it. So what we need to do is we need to actually capture our Z before we do anything. We're going to do var Z index, so our Z, and our path 0. We're focusing on the next in the list. We're going to do transform dot position dot parent dot position dot Z. So we just want to keep a reference to what our node's Z is. Then we're going to do our character dot transform dot position equals vector 2 dot move towards. If you don't do vector 2, what will happen is when you get to like a point of height where a character has to move upwards, you'll see he'll slow down. His speed won't be consistent, and we want to keep that speed consistent. The character will slow down as his Z increases, which it doesn't look nice. Trust me, it doesn't look good. So move towards, and what we need to move towards, our character's current position dot transform dot position. We need where the character's going, so it's going to path 0 dot transform dot position, and we need the speed on which it's going to move, so that's going to be step. And now we're going to do our character transform dot position. We're going to add the Z back in, equals a new vector tree, and let me just copy and paste this a couple of times. Boop, boop, get rid of that extra equals. So equals x dot y and Z index. Okay, so this method will automatically set our character's Z to be 0. We don't want that. So once we've done our step, we're going to set it back, the Z back to what we want it to be. Also with the move towards is that it's very rare that you'll get exactly like 0, 0 equals. So we're going to check the distance as well. If vector 2 dot distance, again, we only care about the vector 2 here because our character is moving at a consistent speed. Character dot transform dot position from our paths, starting nodes position, transform position. If it's greater than, or if it's less than some small number, so dot 0001f can be as small as you want really, but I haven't really put much thought into that. So once our character is close enough to the center of the tile, we're just going to set it so we know his values are exact. So I already have a method called position character that I showed earlier, and it's just literally positioning our character on the tile that we want him to be at. So I'm just going to copy that line. In here, we're going to position our character, and it's going to be at path 0. And then after that, all we need to do is remove our starting node. We move, since our character is already there, so we move at 0. And that's our move along. And I think I might be done. So let's have a look. In Unity, we're going to have a look here. We're going to spawn our character, and let's go 2 across. And no, we didn't move. Oh, why didn't you move? It never worked the first time. And that is because speed is set to 0. So we're going to set it to something like 4. It's probably really fast. Spawn him in. And oh, that looks pretty good. Now our character is moving around correctly. If I click on the height, he will go around the long way. That is pathfinding in a nutshell. And that is where I'm going to leave you there with this tutorial. Part 3, we're going to make this look better. So we're going to display our user's path before we start moving. And we're also going to implement range as well. So our character can only move a X range. So yeah, if that sounds good, make sure to subscribe and like so I know that you want to do it, that you want me to do it. And it should be out very soon, hopefully tomorrow. All of this is pre-recorded, so yeah, hopefully it'll be out tomorrow. But yeah, thanks so much for watching. If you have any suggestions or feedback on this was I would really appreciate it by putting some comment below and let me know. So yeah, cheers guys. See you next time. Peace.